Hi everyone, today I'm going to teach you how to find the center of mass of continuous particles. Now, as we saw in the previous video, the center of mass of a system was given by summation mx by summation m. Now, this m is small but so this is how we found the center of mass for a given number of particles. But what if the system is continuous? What if I say I take a really weird shape and I want to find the center of mass? You can't take the number of points, and this is going to be infinite, right? So what we do is we use something called integration. You all know what integration is. So we use integration. Now you know that when we have a summation of very small particles in a large amount, then it becomes integration. Well, if you don't know, well, you know now. So when you add repeated, or rather when you add a large number of infinitely small particles, so a large number of infinitely small particles. So when you add a large number of infinitely small particles, then the summation, it turns to integration. So for example, if I took a rod, or rather let me start by giving you a general formula of how to find this thing of for individual part for a continuous system of particles. God, I'm so sleepy. So center of mass for a system of continuous particles, I'll give you the formula. It's given by integration of x into dm by integration of dm. Like if this is along the x-axis, if it was along the y-axis, you'd get y dm by integration of dm. And as you can see, you're differentiating it with respect to the mass, because the distance does not, you don't take it with respect to the distance, you take it with respect to the mass, because you're dividing the element into number of small pieces. So how this works, how do we get this formula? For example, if I took this, or rather I'll take a more irregular shape. If I took something like that and I want to find its center of mass, and I say like this is my coordinate plane or something, then what I do, I divide this into a number of small parts. I'm going to just divide into really small chunks. So the number of small chunks is going to be like infinity, right? It sounds fancy and everything, but so what you get is each distance is defined. The distance from the origin for each particle is going to be defined. Say I just take this particle. The distance is going to be defined. So we have x, but the mass is infinitely small because it's an infinitely small particle. So the mass is taken as dm. And dm, when you take d something, it usually means that it's really, 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 really small. So that's why my formula is in integration with respect to mass and not with respect to x. So this is the general formula for getting the center of mass of a continuous system. Let me write that in red. I've heard that red helps people remember more easily. You should try that, So when you integrate this, x is like a constant value and can be taken out, but mass is what you're differentiating with respect to. Let's give it a nice circle. Yes. Now let's take a few examples on how to differentiate with respect to this concept. Let's say I take a rod. This is a simple example of a rod, and say my coordinate plane is over here, and I'm gonna take this width of the rod to be negligible, so it's gonna be like 0. It's more like that than this, but I've just taken as that, Now here this at this point x is equal to 0, and at this point x is equal to L, say if my length of the rod is L, and my total mass is m. Alright. Oh yeah, I want to tell you one more thing. When you take a continuous system, you integrate this part dm. This total mass is going to be nothing but the full mass. So when I it's going to be integration of dm, and integration of dm is going to get me m. So because here I'm integrating the product of the displacement and the mass, but here I'm integrating just the mass. And when I integrate the mass, like integration of dm is nothing but m if you take the limits from 0 to m, because you're covering the whole mass, right? So this is going to be equal to m, and that's what I've done here. Going back, this is our example, right? X is equal to, so from x equal to 0 to x is equal to L. Now how do I find the center of mass of this particle? Firstly, you take say a part over here, and let's say this part is at a distance of x from the origin. I'll take another small part over here, and let's say this distance over here is dx. Alright, that's what I'm doing. I'm going to take x and I'm going to take dx. Now how this works, you'll come to know soon. You know the density of the rod, right? So the density of the rod is going to be nothing but the mass. Oh no, you can't find the density, you'll find the linear density. So the linear density is given by sigma, I think. Not like it really matters, but let's say sigma. It's given by mass per unit length, right? And this is going to be linear density for this rod because it has mass m and length L. So this is my linear density, mass by length. And this is going to stay constant throughout. So this is going to help us a lot. So let's get back to this. dx. What's the mass of this going to be? It's going to be dm, right? An infinitely small particle of, like, say, infinitely small width over here is going to have an infinitely small mass. I'm saying that too many times, but it's going to have a really small mass. So if I want to find the mass of this here, I've taken it as dm, but what if I want to find it with respect to the linear density? Linear density is mass by length, so what's the mass going to be? Linear. So I'm going to use that. So we already know it's dm, so the LHS of the equation is going to be dm is going to be equal to, and I'm going to relate it with linear density over here, and it's linear density into length. What's the length we've taken? dx. So that's it, and it's going to emphasize m dx by L. So this is going to be our small mass. Now we know this, right? We know this, and this is fancy. Now keep this in mind. I'm gonna switch pages because I think I'm kind of out of place. Okay, let me just give you the formula, a small formula. So this is at the x-axis, right? So the center of mass on this is going to be equal to, the center of mass of this is going to be integration of x into dm by integration of dm. Correct? Now keep this in mind, and I'm going to switch. You remember that dm is equal to m dx by L. Why am I writing this? Yeah, m dx by L, and let's keep that aside as 1. And we found that, say, what do we just get? The center of mass is x dm integration by m because integration of dm is m. And so we're going to use this relation of 1 and we're going to put it here. So what does that give us? Integration of m x, integration of x into m dx by l by m. This m and this m can get cancelled. L is a constant, so it comes out. So what are we left with? 1 by L integration of x dx. Now we're going to integrate this throughout the length, right? So you take it from 0 to L. Those are going to be our limits for this integration. So when I expand it, I'm going to get 1 by L into x square by 2, 0 to L. And that is L by 2 when you expand it. So the center of mass for a rod is given by L by 2. Can I write this somewhere? Center of mass for a rod is equal to L by 2. So this is a simple way to derive. So what do? First you find the density, linear density or area density or the volumetric density, whatever you call it. That's what you take first, right? And then you divide it into smaller chunks. You get a small length, you get the small mass of that small length. You derive a relation between the density and the mass, the small mass and the small length, and substitute it in this equation for finding the center of mass. This equation, my bad. So that's what you do. Thanks, and I will see you in the next video with another example.